Okay. Welcome to GADEPS. We have our speaker, Ursula Whitcher. Well, how is pronounced your surname? Whitcher? Or
yeah, that's perfect.
That's perfect. Okay. She's going to talk about Picard rank K3 surfaces, Hasse Witt matrices, and hypergeometric function. So, Ursula.
Right. So thank you so much for inviting me. I'm excited to be at IMPA in spirit, and I hope someday I will be there non-virtually as well. I want to talk today about a story surrounding Picard rank K3 surfaces. And I did write part of this talk for graduate students, and I see that we have lots of experts in the audience, so don't feel shy to speak up and urge me to either speed up if you are tired of the background detail or slow down if I'm glancing at something technical that you'd love to hear more about. This talk is going to be about work that I'm working on with Adriana Salerno, who has tuned in today. So hi, Adriana. And we are seen here at Fields Institute. We've met in very many places all over the world. These are linked concepts that I want to talk about. The underlying structure here is hypergeometric structures, which show up in geometry and also show up in number theory. And the way that they're going to be bound together at the end is through the Hasse Witt matrix. But we're actually going to spend a lot of this talk sort of focusing on the geometry part, which is the piece that I love and know most closely. And so if you're sort of hoping to see the number theory, you should think of the hypergeometric structure as this piece that's sort of carrying along underneath, and that we'll see kind of wrapping everything together at the end. K3 surfaces. K3 surfaces are named for Kumar, Kaler, and Kodaira. Those are the 3 Ks, which I have shared here in all of their beauty and glory. And they're also named after the mountain K2, which is one of the highest mountains in the world. The idea being that they have this really rich and challenging structure. And so there's all of this stuff that you could learn about mathematics as a whole by struggling to, as it were, climb K3. So what do we know about K3 surfaces? If you want the technical definition over the complex numbers, they're simply connected complex surfaces with trivial canonical bundle. And we have our favorite examples that we might carry through. One of them is smooth Quartics surfaces in projective space. You could take certain branch double covers, or the example that is sort of most close to my heart is hypersurfaces in special toric varieties. That's something that we're going to focus on more. Right. K3 surfaces also fit into this tower. There's a tower that has elliptic curves, and then going one dimension up, we get K3 surfaces, and then if we go another dimension up, we get Calabi-Yau threefolds. And so you can think of K3 surfaces either as generalizing things that you know and love about elliptic curves, or as giving you this sort of window into Calabi-Yau threefolds and all of the stories that you might want to tell about Calabi-Yaus. But there are also some special properties that are only special properties of K3 surfaces, and I hope that we're going to see some of those fun special properties as well. Okay. Here's the Hodge diamond. All of the interesting pieces of the Hodge diamond of a K3 surface are concentrated in this middle dimensional piece, where the Hodge row goes 1 and then 20 and then 1. And in particular, we've got a holomorphic 2 form, which is unique up to sort of trivial scalar multiplication that lives over in that H20 piece. And you can see from the Hodge diamond that we have this sort of 20-dimensional piece where we might try to vary their holomorphic form. Now, the Picard group of a K3 surface has rank in between 0 and 20 because it lives both in H2 with Z cohomology and in this H11 piece of the Hodge diamond. You can also think of the Picard group as the Néron-Severi group of algebraic curves, just using Poincare duality. It's always going to be perpendicular to the holomorphic form. So if you have a high Picard rank, you're restricting the possible variations of your holomorphic form that you can take. But the Picard group is really this kind of discrete invariant. And so if you're looking at a family of K3 surfaces, you can have sudden increases within the Picard rank. It's not going to be a smoothly varying thing. That means that if you want to think about how to vary complex structure of K3 surfaces, you can't specify the entire Picard group, because your Picard group can jump around in a family, and in fact we know that it must jump, that it will, for certain pieces of a family, jump as high as it can. But we can choose a free abelian group that we're going to have for all of the members of our family. And we know then that our special specified free abelian group will be perpendicular to our holomorphic form for anything in our family. And in particular, the sort of cleanest case is if we choose a rank 19 free abelian group, then we've only got 1 degree of freedom to vary our complex structure around. And we can say more. If we specify a free abelian group of rank 19 that lives in our Picard group, then our Picard Fuchs equation is going to be a rank 3 ODE. The coefficients are going to be rational functions, and it's going to be a Fuchsian differential equation. So we're going to have really nice singularities and have a really nice kind of friendly classical ODE. And there's even more structure using this idea of a symmetric square. If you have two differential equations, you can look at, okay, what is the differential equation whose solutions look like products of our original differential equation? And in fact, if you take rank 19 K3 surfaces and look at their Picard Fuchs equation, then you get something that looks like the symmetric square of a lower order, of a second order differential equation. The moral being for our purposes, sort of with a geometric mindset, that if you take the Picard Fuchs equation of a family of Picard rank 19 K3 surfaces, this looks like the symmetric square of the Picard Fuchs equation of an elliptic curve. So this dimensional tower that we saw earlier with the elliptic curve going up to the K3 surface, that turns into a Picard Fuchs equation story as well, where for very high Picard rank K3 surfaces, you can see that their Picard Fuchs equations actually look like these lower dimensional Picard Fuchs equations. The specific examples that I'm interested in are motivated by mirror symmetry considerations. So let me just sort of fix the mirror symmetry story that we're looking at. The kind of classical version of mirror symmetry would say that we should have paired families of Calabi-Yau manifolds, and that variation of complex structure on one side of the story should look like variation of Kähler structure on the other side of the mirror relationship. I'm mostly going to be focused on the variation of complex structure side. I think that's the B model side if you're looking at things with a more physical lens. So really classical story continued. For quintics in P3, they have this Hodge diamond that's a bit more complicated than the K3 Hodge diamond. That's got a middle row that goes 1, 101, 101, 1. And then on the mirror side, if you build a construction that will give you mirror quintics, you genuinely reflect the Hodge diamond. That is exactly why it's called mirror symmetry. And your 1s and your 101s swap. So let's build the mirror of a really classical mirror of quartics in P3, just as an example, concrete example to carry around with us. We're going to start with all of the smooth quartics in P3. We know those are K3 surfaces. We're going to look at the Fermat pencil. So we'll take a special quartic. You might also know it as the Doric quartic, depending on how you were mathematically raised, and deform it by a 1-parameter family. This admits an action of z mod 4z squared. So you can see that we can multiply all of the coordinates by fourth roots of unity, but we're in projective space, so it's not really 4 degrees of freedom, it's 3 degrees of freedom. And then we also want that x, y, z, w deformation parameter to be fixed. So that places another constraint on the fourth roots of unity that we can use. We end up with essentially 2 copies of z mod 4z. And then we resolve the singularities and we get our mirror family. That would be the mirror family to all of the smooth quartics in projective space. So thinking about what's going on from a complex deformation perspective, we had lots and lots and lots of possible complex deformations for all of the smooth quartics in P3. On the other hand, we've built this new mirror family, and that kind of visibly only has 1 degree of freedom given by this parameter psi. So thinking about what happened with Picard ranks, we started out with general smooth quartics in P3. Those have Picard rank 1, although it is a little bit of work to write down a smooth quartic that has this lowest possible Picard rank. That's some cool research by Elson, Hans, and Janelle. And then if you want a general member of the Fermat pencil, that has Picard rank 19. So already by restricting to the special pencil, we restricted the Picard group a lot, and we got really special behavior. And the mirror family also has Picard rank 19. So somehow we have these extra relationships between the special pencil and the mirror family, although they're not the same family, although they have the same Picard rank, they have different Picard groups. So this is something that we kind of want to carry forward. We want to study the relationship between the Fermat pencil and the mirror pencil and see what kinds of mathematical properties we can observe and what kinds of things we can generalize. And of course, if you're going to do this really carefully, if you're going to try to understand mirror symmetry for K3 surfaces in general, you do need to understand what's going on with the Picard groups more carefully. And that means that you have to pick what exactly is this lattice that you're going to polarize by, or kind of equivalently, what is the abelian group that you're going to try to see inside your Picard group. So what happens if we try to make this more arithmetic? Well, one thing that we know, this goes back to work by Doric, is that, well, okay, the work of Doric tells you stuff about the zeta function of the Doric family or the Fermat family, and then work of Zeta de la Asa tells us more about the mirror side. And if you look at this, you see that their zeta functions share a common factor of degree 3. And this isn't just any common factor of degree 3. This is a common factor that corresponds to the third order hypergeometric Picard Fuchs equation that you get, that's satisfied by our unique holomorphic form. If you want to know more about shared factors, there's old work by Candelas and Zeta de la Asa and Rodriguez Villegas that looks at shared factors of the quintic and its mirror, the sort of most classical mirror symmetry case. There's work of Shabnam Kadir where she reports this stuff about the quartic that Zeta de la Asa worked out. And then she also looked at some interesting octic Calabi threefold examples. Adriana and I, in collaboration with Chuck Duran and Tyler Kelly and Steve Sperber and John Voigt, thought a lot more about what's going on with shared factors in this quartic case, and then how to generalize it and find all kinds of examples of shared factors. And then there's also work of Kloosterman, who gave a more geometric interpretation to what we had done in 2018 and showed other ways to see where those common factors might be coming from geometrically. This may be a good time to pause and ask if anyone has questions or things they're wondering about.
Maybe about this shared factors. So this is about the zeta function, not the Picard Fuchs equations of dwarf family when you write. I think I remember this Chuck's article who describes all the Picard Fuchs equation attached to the mirror quintic. So there is some relation between the Picard Fuchs equation the other Picard Fuchs equations and the zeta function, I think, or
yeah, definitely. So like this is pulling out one factor that is just the piece given by the holomorphic form, but you can totally ask, like, how do I describe the entire zeta function, and what does that tell me about other periods that are maybe not the holomorphic period? And in fact, that is something that we looked at as well. If you look at just the quartic, that is something that Shabnam Kadir wrote down in her dissertation based on Xenia's work. And then Chuck and Adriana and I and Tyler and John and Steve as well, we worked out what's going on for an entire class of interesting quartic K3 surface pencils. And what you see is you see that all of the other periods that are not holomorphic are satisfying hypergeometric Picard Fuchs equations as well. And then you can look at the entire zeta function, and you can break up the entire zeta function in terms of these non-holomorphic periods. So it's a really interesting, rich structure that's going on there.
Okay.
Is there any other stuff that people are wondering about?
I think you can go ahead.
Okay, cool. All right. So let me try to, I'm going to try to make things more complicated geometrically, and we're maybe looking a little bit less complicated arithmetically for now, which is a congruence that we get if we take pieces of our pencil where our parameter is integral. We can compare the point counts with our original Fermat pencil and our mirror pencil, and over finite fields, these point counts are congruent. Again,
Q is a prime or a power of prime?
So here Q is a power of a prime, and we're going to restrict later on and look just at the prime power, at the prime itself.
Okay, thanks.
Yeah. So morally, this is telling us something about the Picard Fuchs equation. Again, for the holomorphic form, it's telling us that we have this factor in common that comes from the Picard Fuchs equation, and therefore that we have a relationship of unit roots. And this is something that we're going to use as our sort of like first piece to try to see if we can generalize this story about the quartics to new kinds of contexts. So one place that you might want to do this is in the sort of Batarev mirror symmetry setting. So let me talk a little bit about Batarev mirror symmetry and try to maybe fix a notation a little bit. So we're going to take a polytope in, generally it could be as many as k dimensions, that has facets that are given by certain hyperplanes. And we're going to take two lattices. Lattice of points with integer coordinates in Rk, which we'll call n, and then we'll have a dual lattice in another copy of Rk. And if we have a lattice polytope, we can write down all of the facet equations for our lattice polytope. And because it is a lattice polytope, we can take the normalization that the right-hand side is -1, and all of these A1s are some rational parameters. And our polar polytope will just be the polar polytope that has vertices given by reading off the coefficients from this normalized facet equation. We're going to say that a lattice polytope is reflexive if this new polar polytope is also a lattice polytope. This is a dual kind of relationship in the sense that if you take the polar or the polar, you get back where you started. And we can say that these two polytopes are a mirror pair of polytopes. So here's an example. Some friends, we've got a sort of square pyramid here, and then when we take the polar, we get a reflexive polytope that has lots more lattice points in it. So you can classify these things up to changes of coordinates preserving the lattice. There is only one in 1 dimensions. It's just the interval from -1 to 1. There are 16 of these things, 16 reflexive polygons. There's 4,319 in dimension 3. There's 473 odd million in dimension 4. And in higher dimensions, it's an open problem, although we do know quite a bit about various special types of reflexive polytopes in higher dimensions. Now, we can use a polytope to make a toric variety, making it up out of cones. There's a couple ways to start with a toric variety and get a fan. You can take either the normal fan, or you can take the cone over the faces. I personally, because I'm used to working with reflexive polytopes, like to just take the cone over the faces. So you imagine starting at the origin, drawing a ray out through each of your vertices, and then you get cones corresponding to each of the facets of your polytope. Using this, we're going to describe a toric variety, which is n-dimensional if we're working in n dimensions, or k-dimensional if we're working in k dimensions. And these are going to be compactifications of C star to the n. So let's do a quick example just to sort of get our hands on the notation. Our standard simplex has vertices 1, 0, 0, 0, 1, 0, 0, 0, 1, and then a -1, -1, -1. So it's going to be some kind of triangular pyramid, also known as a simplex. You can think of P3 as given by C4, you remove some stuff, and then you mod out by an equivalence relation. In the case of P3, we're just going to remove the origin. But for a general toric variety, we could remove some more stuff. And then we need to define the equivalence relation as well. So how are we going to do this? These coordinates Z1, Z2, Z3, Z4, those each correspond to the rays in our fan that we got from the vertices of our polytope. So we can see here we've got 4 different vertices of our polytope. And then we've got one equivalence relation. And the reason we've got one equivalence relation is that we've only got one integer relationship between our vertices. You can, if you add up 1, 0, 0, 0, 1, 0, and 0, 0, 1, well, adding on -1, -1, -1 to that exactly gives you 0, or I guess I could have written that as vector 0. Now, on the other side, we've got this polar polytope, which has vertices 3, -1, -1. And you can see that it has lots more lattice points on our polar side. And if we run the same program to get us another toric variety, what we get out of it is a resolution of P3 modded out by Z mod 4Z squared. That 4 is morally coming from the fact that there's a sort of lattice distance of 4 along each of these edges of this polytope. Now, that's just giving us toric varieties, but I actually want to look at hypersurfaces. So what I'm going to do is, for each lattice point in my polar polytope, I'm going to choose a parameter. And then I'm going to make one monomial for each of the vertices. Right, so for each, I've got a monomial for each lattice point in my polar dual polytope, and I add up over all of the possibilities and I get some kind of polynomial. So again, my variables look like lattice points in my original polytope. My monomials look like lattice points in my polar dual polytope. So you've got this polynomial construction that's really giving you a tight relationship between each side of your mirror relationship. Now, if we use the fan over the faces, the way I drew the picture earlier, or equivalently, you can take the normal fan to the polar dual polytope if that's friendlier to you. We get a Calabi-Yau variety. This Calabi-Yau variety might be singular, so we need to potentially smooth it out a little bit. As long as we're in ambient dimension 4 or less, we can smooth it out enough to get a smooth Calabi-Yau in all cases. And then if we flip what we think of as our regular polytope and what we think about as our dual polytope, that gives us paired families of hypersurfaces, just changing our point of view about what's the original and what's the mirror polytope. These are indeed mirror families of Calabi-Yau varieties. So that's how it works for three-folds. And if we have three-folds, we can further get a GKZ, or sometimes called an ahypergeometric system of partial differential equations that gives us the periods. This is nice and combinatorial. You can use your polytope to get the description of your GKZ system. And GKZ systems are again linked to classical hypergeometric series. And in lots of cases, you can even get a basis of hypergeometric solutions for your GKZ system. So if you're looking at the sort of general anticanonical hypersurface, this is really naturally related to the GKZ system. Let's look at quartics. So here, if we take the standard simplex, and we look at this general monomial family, general anticanonical polynomial that I wrote down for you a minute ago, we get all of the quartics in P3. And then if we look at the polar dual and we run the same game again, we're going to get the mirror quartics, which will be naturally only a one-parameter family up to some kind of overall identification and simplification. But you can ask, what about the Fermat pencil, right? When we built the green Plesser mirror, we didn't just have all of the smooth quartics. We also had a special pencil that was our diagonal pencil or our Fermat pencil. And so you might wonder, can I also see what's going on with that inside our polytope? And can I sort of reach out and grab this thing combinatorially? So the answer is yes, you can. And the trick is, instead of taking a monomial for every single lattice point in your polar polytope, we're just going to take the monomials that look like the vertices of our polar polytope. And then if we want a one-parameter deformation, we're going to deform by the monomial corresponding to the origin. In this case, I just threw in a plus psi. You know, you can do an obvious change of variables and make it -4 psi, which in some cases makes things work out a little bit more prettily. And this gives you a generalization of your Fermat or your Doric pencil in PN. We now see like the Fermat or the Doric pencil would come from taking the standard simplex and its polar dual. But if we took other reflexive polytopes, we can potentially get other one-parameter deformations that are really combinatorially natural and that act in some sense like the diagonal pencil that we know really well. Any questions here just quickly about the setup, since this is kind of a lot of notation?
What is K here in this?
So K here, we're running potentially just up to the number of variables that we have in our homogeneous coordinates. So we have one variable in our coordinates for every lattice point in our polytope if we resolve singularities.
So surely it will be more than 4, yeah? Or...
It depends on the polytope that you're working with. So like if we're building projective space, we took the fan over the faces of the standard simplex. So that just has our 4 vertices. Going back for the picture for a second, it's the 4 vertices here on the left-hand side.
Okay.
But yeah, potentially you can get lots more, right, depending on the complexity of your polytope. And in general, you would expect lots and lots.
I think
Thanks.
like classical work, even if you put coefficients for these monomials, at the end the moduli space is just one-dimensional, governed by this psi. It doesn't matter more coefficients on this monomial because you took sum of monomials and all the monomials have coefficients 1. I see. Okay.
Okay.
Okay. So I want to look for some criteria that will let me pull out things that will maybe act a little bit like the example of the quartics in P3 in their mirror. And one thing that you might notice if you look at the standard simplex in its mirror is that they are both simplices. In the 3-dimensional case, in other words, they are both triangular pyramids. It's just that on one side you have only a few lattice points, and on the other side you have lots and lots of lattice points. So if you try to phrase the general criterion of like, what does it mean to be both simplices but with different numbers of lattice points, you end up looking at something called combinatorial equivalence, which is just saying, okay, we've got the same kind of face structure, the same kind of number of vertices and edges and facets and so on, and the inclusion works the same way. So here are some pictures of a group of things that are all combinatorial equivalent. In this case, these are all square pyramids, but they have different kinds of lattice point structure for each of them. And then you can go looking for things that act a little bit like having an overall quotient relationship. When we built the mirror for the simplex, or really even just for the Fermat example, on one side we had P3, on the other side we had a finite group quotient of P3. So you could ask, okay, where can I find this kind of finite quotient relationship in more complicated situations? One thing that you need here is combinatorially equivalent. You also need a slightly stronger relationship, which is we need the same integer relationships between the vertices. And just to show you what that looks like in practice, let's go down to 2 dimensions for a second. Here's the diamond and the square. The diamond and the square, or if you want to say the cross polytope and the 2 cube, to be more technical about it, these each have 2 pairs of vertices that are opposite vertices that sum to 0. And this would give you a product of projective spaces on one side and then the mirror of product of projective spaces on the other side. And you can prove a cute little lemma. This is something that I worked out when I was in Wisconsin with an undergraduate student, that if you have reflexive polytopes that satisfy this quotient criteria, then you get Picard Fuchs equations on each side of these generalized diagonal pencils that are the same Picard Fuchs equation. So this really feels like the Green-Plesser mirror construction, that you have now 2 potentially different families living in potentially really very different spaces, but you're able to pick out, using this natural combinatorial criterion, of families that are going to give you the same Picard Fuchs equations. So this is the kind of set of examples that we're going to be curious about, seeing how much we can push through. And to do this, we're going to use the Hasse Witt matrix. So let's suppose we've got a smooth variety over a finite field of some prime power order. You can look at how the Frobenius operator acts on its cohomology. It's going to give you some kind of p-linear map. And the Hasse Witt matrix is just a matrix for how the Frobenius operator acts on this kind of cohomology space and whatever your favorite basis is. Now, of course, we're looking at Calabi-Yau's, where this cohomology group is really simple. And so the Hasse Witt matrix is kind of misnamed in this situation. We've simplified down to really nice spaces, and so we just get a one-dimensional matrix. And we can try to understand how Frobenius is acting on cohomology in this setting. And we'll be looking at basically really just a number, but it's a one-dimensional matrix. Nick Katz found that the number of points on a Calabi-Yau variety mod P is going to be determined by its Hasse Witt matrix. And he gave us information specifically if you're looking at hypersurfaces in Pn. In that case, there's a nice way that you can genuinely compute the Hasse Witt matrix. You just look at the coefficient of a particular monomial raised to the p minus first power when you raise the entire hypersurface equation to the p minus first power. So that's really nice and computational, and again, combinatorial. In particular, he looked at the Fermat pencil. I guess he called it the Doric pencil because he's a number theorist. And he found that if your powers of your variables and the prime that you're interested in are relatively prime, then the Hasse Witt matrix is going to be given by a truncated hypergeometric series. But in fact, that hypergeometric series corresponds to the Picard Fuchs equation. The Picard Fuchs equation is a hypergeometric differential series, a differential equation. Its solution is a hypergeometric series, and truncations of this series are going to exactly give you the Hasse Witt matrix or the Hasse Witt invariant. So toric version. People have thought about it. One of these is Masha. I was really stoked to see Masha tuning in today because I knew that we were going to talk a little bit about her work, who has collaborated with Fritz Beukers to give a really sophisticated way of thinking about the Hasse Witt invariant and some generalized versions. Another person who has thought about trying to get this in the toric setting is Chenglong Yu, who worked on this in his dissertation. And so I'm going to talk today more about the formulation that Chenglong Yu and his collaborators have done, but I hope we will all be back here next week to look at what Masha did and to see Masha's take on it, because I think that's really interesting as well. So how did Yu and Huang and Lian and Yao formulate this? Let's look at a Calabi-Yau variety that's realized as a hypersurface in a toric variety. In that sense, we can write down the Hasse Witt matrix as a polynomial in AI, which are, in this case, this is the information that we have about our hypersurface. This is just the notation that they use. So the Hasse Witt matrix is a polynomial in our hypersurface variables of degree p minus 1. We can write down the period integral in terms of a Taylor series given by our polynomial information. And the Hasse Witt matrix is going to satisfy a truncation relationship. That's just a truncation of this Taylor series at an appropriate degree. So if you have information in general about your hypersurface, you know everything about the Hasse Witt matrix. This is a cool theoretical paper that's telling you a ton of stuff, but they really didn't dig into the examples at all. There's sort of all of this potential to study interesting and meaningful examples, and HLYY do not tell you anything about any example except for the hypersurfaces in projective space that go all the way back to Katz. So it's really kind of like necessary and fascinating, like once you have this theoretical edifice to kind of chew into it and see what kinds of things you can learn in practice about examples of interest. So that's one of the things that Adriana and I did in our paper that's on the archive, is we took combinatorial equivalent polytopes. We looked at the generalized diagonal pencils, the sort of generalization of the Fermat pencil that we've been looking at. And we said, okay, well, if we've got two diagonal pencils where the underlying polytopes satisfy this toric quotient criteria, we know their Picard Fuchs equations are going to be the same. That means that their Hasse Witt matrices are going to be the same. And therefore, are the Hasse Witt matrix, well, if their polar polytopes satisfy this relationship, the Hasse Witt matrices will be the same. If the original polytopes satisfy this relationship, then the Hasse Witt matrices are going to be, if not the same, at most different by an integer not depending on psi. And in particular, we can use this to get a relationship that feels like this point counting relationship. If we do our point counting over here, just over a field of prime order, the point count is going to be the same mod p on each side.
Ursula, what was this toric quotient criteria?
Right. So remember, we want two things. We want the polytopes to be combinatorially equivalent. So essentially the same general shape of the polytope, just in terms of how do their vertices, edges, faces, more generally, and faces relate to each other. And then we also want the same integer relationships between the vertices. So if we have some kind of relationship that says an integer times this vertex plus an integer times this other vertex plus, dot, dot, dot equals 0, we need that system of integer equations to be the same for the vertices on each side.
Okay, thanks.
Yeah. And so maybe that's easier to see in an example. Here are 4 polytopes that satisfy the toric quotient criteria. These are all sort of square pyramids, if you will, or rectangular pyramids. So in that sense, they're combinatorially equivalent, but they also satisfy the same relationships among their vertices in the sense that you can take the same integer combinations of their vertices, add them up, and get 0. If you build this one parameter deformation of these using these polytopes, the polynomials that you get can look really different. So here are a couple of examples just for 2 out of the 4. You can see that in some cases you get a polynomial that looks relatively tractable and relatively simple. And in other cases, you get a polynomial that's just like a huge mess. It's got 10 or 11 different variables running around, all kinds of different stuff. But the nice thing is, because we have this theoretical information, we can use stuff about the simple polynomial to extract information about the arithmetic properties of the complicated polynomial. In particular, we can work out the Picard Fuchs equation. So here's the Picard Fuchs equation. If you do an appropriate change of variables, it's hypergeometric. Really pretty classical hypergeometric kind of things with 1/3 and 6ths. And if we mash with the HLYY setup, which means that we're going to expand around Maxwellian uniform monodromy, we get another, even prettier, in fact, classical hypergeometric equation, this time just with 1/2 and 1/3 and with 1/1 as our beta parameters. And we can write down this gorgeous expression for the point count. Mod P, our point count is just given by this truncation of our classical hypergeometric equation, series solution. So that's kind of cool and kind of powerful because you have your Picard Fuchs equation, which you work out, and you get from that this expression that'll tell you what is the point P, mod P point count for any of these pencils from any of these 4 different polytopes. And I want to point out that we are specializing. So for instance, if we started with our first polytope, the sort of fewest lattice point polytope in that system, a general K3 surface in that toric variety would have Picard rank 2, and its holomorphic period would satisfy a fairly elaborate GKZ system of equations. On the other hand, we've specialized down to something that's Picard rank 19, and that satisfies a spot-on hypergeometric Picard Fuchs equation. You can imagine maybe embedding yourself in a set of several combinatorially interesting polynomial families and kind of specializing up and down. That's something that Hossein and I and Chuck and Andrew Harder have looked at in particular situations. But we have this potential for maybe broader toric variety exploration of, hey, what happens if we specialize starting with something that's a GKZ system and going all the way up to a particular hypergeometric story. Okay, so we got some arithmetic information. In general, it's really hard to count points on K3 surfaces. It's kind of ongoing theoretical and computational work to find good algorithms to do that. Because we knew a lot about the periods and because we had both combinatorial and arithmetic information about the periods, we got this really fast way of computing arithmetic information. And it worked for multiple families, for not only the families where the polynomial looks nice, but also for families where the polynomial is a giant mess, and we maybe wouldn't want to try to directly compute with that polynomial family. And I want to end maybe with this kind of fun hypergeometric fact, linking back to a particular thing that we know about our rank 19 K3 surfaces. And that is Clausen's identity. Clausen's identity, I don't know if you can hear the cat in the background, but the cat is excited about Clausen's identity too. Says that you can square a 2F1 hypergeometric series and get a 3F2 hypergeometric series. In our particular Picard Fuchs equation example, you would square a hypergeometric series that has 1/6 and 5/6, and you would get out our example of interest with 1/3 and 2/3 and 5/6. So then you can ask yourself, okay, we know that the Picard Fuchs equation looks like a perfect square. Is it true then that the Hasse Witt matrix of our Picard rank family is also a perfect square? And it's really tempting to say that it should be yes, because we know that the point counting is controlled by the Picard Fuchs equation. But it's actually surprisingly interesting and subtle. It's a perfect square sometimes. In this particular example, it's going to be exactly a perfect square, or if you prefer, a quadratic residue, when the prime is equivalent to 1 mod 6. And we have similar restrictions for any hypergeometric Picard Fuchs equation obtained in this way. So if you're going to try to dig into this and ask, why is that happening? Why is it that we don't always have a a quadratic residue Hasse Witt matrix sort of all the time? The answer is that we need some kind of finite field version of Clausen's identity. And indeed, there is a finite field version of Clausen's identity. It's due to Evans and Green. But it depends on the existence of finite field versions of hypergeometric functions, which are defined using multiplicative characters. We've been thinking here just over fields of order P, but more generally, multiplicative characters on fields of prime power order. And if you don't set some kind of divisibility condition on your field, on your prime, then you might just simply not have the characters, and therefore you might not be able to convert what you know about classical hypergeometric equations over to the finite fields that we're really interested in. However, you can certainly hope to extend the Evans and Green result using more sophisticated modern versions of finite field hypergeometric functions. And that's something that Adriana and I are really interested in doing, is saying, hey, can we characterize what goes wrong with this error in general? So I have only 5 minutes left. I could tell you a little bit more about modularity, but maybe I should stop here and we should go back and maybe chat a little bit and see if there are questions.
Okay, then okay. So it is finished?
Yes.
Yeah, okay. So any question? So as usual, we will have two
I have
questions.
okay.
Yunus, go ahead.
So you talked about the integral periods that they can be written in the Taylor series with integer coefficients. I'm wondering if they are modular forms or something like that.
Yeah, so in this case, they do relate to this really pretty modularity kind of stuff. Essentially, you look at the square root of, if you will, right, the 2f1 that squares, and that gives you something that looks like the Picard Fuchs equation of an elliptic group. And then you can go in and try to identify what's going on with the modularity there. In this particular example, what you get is you get gamma naught of 3 plus. So it's a classical modular group, including all of the accumulator involutions. So yeah, in these particular examples, they are modular and they're really nice classical modular things.
Thank you. So they have arithmetic properties also? Or?
Mm-hmm.
What I have any other question? I have actually one question. So I was wondering, you know, this 14. Maybe I have to say to Sergey that because of he entered at the end. Okay. Anyway, there is this 14 examples of Chuck and Morgan, and this 14 examples is divided to 7 plus 7, and there are a lot of criteria to say that to make this this division between 7 and 7. For example, the monodromic group and so on. I was wondering if this Hasse Witt stuff. It's possible to make this distinguish between 7 and 7. I mean, to make the same division of a 14 to 7 plus 7.
That is not a question that I've thought about, but that sounds like a really interesting question to look at. I don't know if it's a fine enough invariant. I don't know like how much it would be able to catch, but it totally sounds like it would be worth looking at.
Okay.
I have a question also.
Okay, Pasha.
So in your main theorem, there is this element n in the finite field, right? That Hasse Witt matrices differ by n, or do I remember it correctly?
Yeah.
Are they 1 by 1 matrices? Why is it just one element? All right. So then my question is, Hasse Witt matrices are mod P reductions of some things that are defined in characteristic 0, like some periodic Frobenius matrices, right?
Mhm.
And we can live them quite canonically in the toric setting. Did you try to lift your invariant n? And my question in general is, have you seen this invariant somewhere else, or is it totally new?
So in the particular examples that I was looking at, let's see. So I think I should say, first of all, I think it is possible that n is always 0. I don't know if it is a genuinely interesting invariant or if we actually have equality. It shows up in the proof because you're essentially running a sort of differential equations argument, right? It's like existence and uniqueness of differential equations, and you know that the Picard Fuchs equations are the same, and so they can be off at most by a constant. And so that's sort of the constant that shows up. And it isn't clear to me if it can be a...
Okay, then
yeah.
I see. Thank you.
Okay, so if there is no question in the recorded session, I stop recording and I ask again if there are questions, so the people feel better to ask questions.